Hey everybody, in this video we're going to be going through an example of how to derive a schematic from HDL as well as an example of logic minimization. Specifically we'll be going through example 4.1 from the book Digital Design and Computer Architecture, the ARM edition by Harris & Harris. Below here is the actual question from the book. So it reads, sketch a schematic of the circuit described by the following HDL code. Simplify the schematic so that it shows a minimum number of gates. So in this with VHDL example, it's pretty straightforward. You have three inputs, A, B, and C, and you have two outputs, Y and Z. It's a combinational architecture, as in there's no clocks involved. It's completely combinational. And so it's a straightforward question. The first part is just to derive the schematic from this VHDL here. And so for Z, for example, you have A and B, so there's an AND gate. And then in the second parentheses, you have not A and not B, so you have two inverters, as well as another AND gate. And then finally, you'll have an OR gate to connect the outputs of the two AND gates. So you can do a similar exercise for Y. And eventually what you would get is a diagram, a circuit diagram that looks like what we have here on the right. And the way that this is drawn is we have the three inputs A, B, and C on the top here, and the outputs Y and Z on the right. And so we went through the example of Z. We said that there would be two inverters. Here they are. We said that there would be two AND gates. Here they are. And then connecting the outputs of the AND gates are an OR gate. So that's part one of this question, the schematic from this HDL. The second part of the question is to simplify the schematic so that it uses a fewer number of gates. So in this case, the minimum number of gates. So what we'll do is first, we're just going to write out these equations for Y and Z in equation form rather than as text. So for Y and Z, when you write them out, they'll look like this. And then what you'll do is notice that Y and Z are in sum of products form. So what you can do after that is write yourself a truth table. Again, there are three inputs, A, B, and C, and because there are three inputs, you can have a total of 8 different input combinations from 0, 0, 0 all the way to 1, 1, 1. So again, sum of products form. So specifically, if you look at the example for Z, you have A, B. So when A and B are both high, Z should be high. So we look for A and B both being high. So it happens to be these two cases down here for 1, 1, 0 and 1, 1, 1. So Z would be high for both of these cases here. And in addition, Z is also high when A and B are both 0. And so that is the case for the first two cases in this truth table, where the inputs ABC are 0, 0, 0 and 0, 0, 1. So again, for these cases, Z will be high. And then for every other case, Z will be 0. You will repeat this example for Y. And so for the Y expression, there are a total of 3 terms, sum of products terms. So you should expect to see a total of 3 ones in this truth table, and then everything else should be 0. So now, once you've got this truth table defined, you'll go ahead and construct your Karnaugh map to minimize this logic. So for Y, the Karnaugh map looks like what we have. Karnaugh map looks like what we have here. So we have A and B as the rows going down, and then the input C going horizontally from left to right. And again, remember for Karnaugh maps, the special trick about them that makes them work is that the inputs are listed sequentially in gray code order, meaning that only one input changes at a time. So you go from 0, 0 to 0, 1, 1, 1, and 1, 0. And for C, it's more straightforward as you go from left to right, since it's just one input in this case, so you just have your 0 and 1. So to fill out this truth table, or rather this Karnaugh map, look at the truth table that you have on the left. Find where this output Y is high, and that happens when the inputs A, B, and C are 1, 0, 1. So A, B, 1, 0, and then Y being 1, so there's the 1. You'll do the same thing for these two other inputs, 1, 1, 0, and 1, 1, 1, and that would result in a Karnaugh map, a populated Karnaugh map that looks like this. You'll have a total of 3 ones, just like you did in the truth table. Everything else is 0, and for the purpose of clarity, I've decided to leave those out. Now remember, for Karnaugh maps, after you've filled it out, you want to circle all the powers of 2 of ones that are next to each other. In this case, there are a total of 2. So you see this first, the 2 ones here are together, and then vertically you've got another 2 ones. And when you write out the expression for these 2 circles, you'll look at the first circle, the horizontal one, which is the case when A and B are both 1, and then C in this case you'll leave out because it changes, and because this circle is here, it means that it doesn't care about the value of C. As long as A and B are both 1 or high, Y is also going to be high. And for this vertical circle here, it is high when A is 1 or high, and C is high, and it does not care about the value of B. As long as A and C are high, Y will also be high. So you've got your sum of products again, and the expression is given down here, Y is equal to AB plus AC, and this will match what we have in the Karnaugh map here. Similarly, we construct the Karnaugh map for Z, same gray code order, and then you populate it based on your truth table for your Z values, same way that you did it for the Y table, and that will result in a table that looks like what we have here. Z is high when A and B are both low, so there's a term here, A bar, B bar, and then Z is high when A and B are both high. So there's your other product term here, A and B. So now you've got a minimized expression for each of the output terms, y and z. And you'll see that AB is a common term between them. Therefore, you don't need to compute the product of A and B twice. You can do it once and then share them between the two outputs. Next step is to turn this into a schematic. So again, our inputs A, B, and C are on the top here. Outputs Y and Z are on the right. And we'll take a quick look at this and see that this first AND gate will produce the A and B term from our inputs A and B. And then the output of this AND gate is shared between the two outputs. So this output from this AND gate will go to the first OR gate, and it will go to the second OR gate, representing this term, this intermediate term that is shared between the two outputs. And this will conclude the problem, and we'll take it one step further, and we're just going to compare how much better this minimized design is to the original schematic that we produced in part 1 of the question. So down here is the original schematic that we had from part 1, and what I've gone ahead and done is listed the number of transistors in each of these gates, and then when you sum up the total number of transistors in this case, you get 44. And then on the right here is our minimized case. So again, all the numbers of transistors per gate are listed, and when you sum them up, you have 24. So there's a pretty drastic difference between the original schematic and the final schematic. Specifically, you went from 44 transistors down to 24, and that's a good improvement. Thanks.